Hello everyone. So far we have covered the topics related to sequence alignment. We got introduced to various algorithms that we can use in order to find our, for example, scoring metrics. And today we are going to talk about statistical significance of alignments, because it's important to know whether our algorithm is working better than other algorithms or not, or even the one that you have developed is even good or bad. How can we measure that? That's why we need to go through this topic, which is an important one. In statistics, before analyzing your data, it's important to know how to summarize them. And when it comes to sequences, let's see what we can do. For example, assume that you are interested in finding ACC codon in your sequence. So in that case, I should go through all my sequence in order to find this codon. And for example, I can summarize it like this. For ACC, I've seen 16 times ACC codon inside my sequence. So this is a type of information that I'm interested in, to see how many times this one occurred inside my sequence. The other thing which would be interesting is the position of this nucleotide. Like for example, A, where did it start? For each codon, you consider the first nucleotide as the position of the codon. So for example, 1, 2, 3, 4, 5, 6, 7. So at the 7th position, you can see that A happened for the first time. So you can define a set to specify exactly at which position the codon started. And this information is also interesting for us to record, because when you want to compare it with other sequence alignments, then these positions could be very useful. So this is just one of the way that we can summarize our sequences. So as you can see, it could be even different methods, even just for one nucleotide, maybe you are interested, or maybe for local alignments, you are interested in, for example, length of 10 number of nucleotides. So you can define it differently. But this is just an example to show you what we can do in terms of summarizing your sequence. Here you can see percent identity. In one of the slides before, we saw that we use this term, and what it means that what's the relative frequency that you guessed your first sequence correctly. Or in another word, if you are just comparing two sequences together, what's the similarity percentage between them? Like, do we have 83% total exact match? Do we have that, 83%? Do we have 10% match? We don't care what if the mismatch is either gap or a mismatch like letters, the mismatches of the letters. In that scenario, you can define percent identity easily. But is it a good method to just use percent identity to know, for example, two genes are homologs or not? And the answer is definitely no, because sometimes just 10% similarity is good enough for us to conclude that these two genes are homologs. And sometimes even 80% similarity is not good enough. So there should be other measures in order to conclude such a thing. And of course, this is useful anyway to find such a percent identity, to say what's the similarity. It gives us idea, at least for comparing the exact genes with other genes. So, but it's not good enough. The other question, is statistical significance good enough to conclude two genes are homologs? So the statistical significance, of course, it will makes things much clearer for us. But still, we cannot say 100% we are sure about that, because if you remember from your statistics course, when we have a measure like, for example, p-value or any probabilities, any confidence interval, we are talking about probabilities at the end, and we have error. Like, for example, 95% I'm sure this is true. Again, 5% I'm not sure. This is not guaranteed that this is true. But still, it's much better than just checking the similarity between two genes. So statistical significance are very useful in order to compare different algorithms together, different alignments together, but it's not 100%, and from the beginning we should be careful about it. Now, assume that we want to compare our algorithm with other algorithms. So let's say I want to check it with just a random algorithm. What does it mean? It means that if you randomly just simulate one sequence and compare it with any other sequence of, for example, nucleotide, then if the random algorithm gives us better result, so it shows that your algorithm is not good, even if they are giving almost the same answer. So it means that your algorithm is almost random anyway. Even if you have a logic behind it, still it doesn't make the result better. So that algorithm is no good. That's why we try to make our algorithm better and better and far from a random algorithm. So how can we test if our algorithm is better or worse than a random one? In statistics, we have a term named hypothesis testing, which is very useful for doing that. And I will show you in the next slide how we can do it. And again, for another question, like not just for random algorithm, I want to check my algorithm with, compare it with other algorithms which are known, maybe they are famous, or someone else has just proposed that one. So how can I compare them? I will show you in one slide that how we can do it using hypothesis testing. And we have a term named e-value. Let's see, what is it? Expected number of sequences that will produce same or better score by chance. So if you are dealing with one database, inside this database they have data related to different sequences which were produced maybe randomly, maybe by other algorithms. And if you come up with a specific sequence, then this database is able to compare it with the existed one and try to understand how many of them were already there, and maybe which are equal or better even than the sequence that you're proposing using your own algorithm. So when you define such e-value, then it means that the higher it is, this is problematic for us, because if you are proposing a sequence which is very good and comparing to other algorithms it works better, then e-value should be lower, so that in the database they cannot find better sequence alignment than that one. So it could be a measure, but this is again not 100%. Sometimes we find high e-value, but your algorithm works better for other sequences, right? So it's more complicated than that. But anyway, e-value is a good measure for comparison anyway. So the bigger your database is, you will get bigger e-values. Why is that? Because inside this database, they already have more sequences that they can produce. And if that's the case, then of course you expect higher e-values. That's why this e-value is not as good as p-value inside statistics. P-values can be used as an efficient statistical significance measure. So personally, I prefer p-values to e-value, and in one slide, I will explain why. Okay, let's talk about a little hypothesis testing, which is the main component, I would say, about the statistics. Because if we learn about the statistic, at the end, we are interested to analyze our data. And we should test different claims. And what we do in hypothesis testing, we claim something, like, for example, my algorithm is better than others. And usually, in hypothesis testing, we consider equality as H0 not equal in H1. That's just a rule that we use in hypothesis testing. So what we are doing, we consider our claim as H0, null hypothesis. We say, for example, my algorithm is almost equal to a random one. This is the claim. And what we want to do is to reject this one, because if you reject it, it means that your algorithm maybe is better or maybe at least different than a random one. Or, for example, you can define H0 as, for example, your algorithm is not as good as the random one, and then H1, the alternative hypothesis, as your algorithm is better than the random one. So to know about such hypothesis testing, I suggest you to go through this video that I provided for you on Auto class. This one is related to our statistics course. This is optional because I'm not going to ask you about hypothesis testing directly. But in order to understand what we are doing in terms of algorithm comparison, it's very interesting to know about it. And at the end, our goal is that you guys can apply it in your research in the future. So it's very useful to know about them. But what we are doing here, like, for example, if H0 means that your algorithm is not as good as random one and H1 is better than the random one, so you will explain it on different distributions. And let's assume that this is a normal distribution. In that case, you will have for sure error anyway. Like, for example, you want to decide until 5% error, I'm fine with it. If I want my confidence interval to be 95%, then 5% I will have error. Based on the error that you define, and we call it significant level, you define alpha. Alpha is your error, your significant level. So under the curve of normal distribution, you can show the significant level based on the way you define your alternative hypothesis. You can watch related things about it, and on that video I explained everything there. So what is p-value that we mentioned earlier? P-value is related to your test statistic. We have a term named test statistic. We calculate it based on the distribution that you have. Then you should know whether that test statistic falls inside the rejection area, rejecting H0, which proves that, for example, your algorithm is better by accepting H1, or non-rejection area, or acceptance area. So test statistic is on this x-axis. It either happens to be here in this area or on the left side. So what is p-value? Based on the test statistic, you can define the area under the curve related to test statistic. Let me show you maybe with a pen. For example, if your test statistics happens to be here, then you will have an area under your curve. And this one is a p-value. And for sure, because this is a probability, it should be between 0 and 1. The whole area under this curve is 1, the whole area. So whatever you will find for sure would be between 0 and 1. So if your p-value is here, it means that your p-value is bigger than alpha. So in that scenario, you cannot reject your H0. But if it happens to be, for example, test statistic is here, your p-value is this area. So in that scenario, p-value, sorry for the terrible handwriting by using a mouse. If p-value is less than alpha, and in that scenario, you reject your H0, which is null hypothesis. As I said, for the time being, I don't ask questions about hypothesis testing because we evaluate you guys for a statistic in another course for a statistic. But it's good to know, at least when we talk about p-value, what do I mean by that? And how accurate is this comparing to e-value? And why I prefer that one. So if you are interested to know about this, please go through the video I provided for you related to hypothesis testing. Probability and expected values in pairwise sequence alignment. What's the probability of a successful single nucleotide match? So let's say I have a sequence for my nucleotides. This is the first sequence, for example, and it continues. When I put 3 dots, it means that it continues. I use the same method in our assignment. And for example, this one, we have this. Okay, now the question is, what's the probability of a successful single nucleotide match? It means that what's the probability that this one is a match with this one? What's the probability that this one is a match with this one? How can we calculate that? This is good to just fix one nucleotide. Let's say, for example, my first nucleotide is A. Then what's the probability that the nucleotide in the second sequence is exactly the same than this one? Can you guess? What are my possibilities? I have 4 nucleotides which are the possible answer. So only one of them is a match for this one, which is A. So it is 1 over 4. So this is a simple probability question, right? Or what about the single amino acid? We have how many of them? We have 20 of them. So in that scenario, the probability is 1 over 20. So as you can see, you fix one of them and you find the probability corresponding with this one. And even we can ask different questions like, what's the probability of the first 2 nucleotides are 100% match to the second one? So what's the answer of this one? 1 over 4 over 2. In terms of amino acids, 1 over 20 over 2, right? So we can ask different questions. Or what's the probability of having, for example, at position 5, nucleotide C, and at the same time having, again, the 100% match for the second sequence? So again, we are talking about this case, okay? So we should be careful about such questions. And again, if we talk about the length now, what's the probability of having TCC? Then things can be complicated, right? So we will talk about the formulas related to that. So probability of and expected values in pairwise sequence alignment, we continue. And what's the expected value of one successful amino acids match in a pairwise sequence alignment of S1 and S2? And let's say, for example, the size of S1, I show it with this notation. The size of first sequence is 5, the size of second one is 10. And the formula is the probability multiplying by my possible cells that I can create in my matrix. So it is 5 multiplied 10, the size of S1 and S2. What is this probability? This is 1 over 20. We talked about it. For 100% match, for pairwise sequence alignment, and this is the probability. Now, if we say 2 successful amino acids, And I showed you before why we power it by 2. So in order to talk about expected value, we are not talking about probability anymore. So the answer is not necessarily less than 1 or more than 0. It could be for sure a positive value, but it's not a probability. Now, let's talk about matching run in a sequence alignment. Assume the following. Interested length of matches, assume that this is denoted by L. Now we have 2 sequences, S1 and S2. The size of them are M and N. And let's denote expected value of L by DL. And how we can approximate the expected value for L. All of them have proofs for sure. If you are interested, you can find the proof for them. But if you are interested in using the formula, you can use this formula easily. So again, the size of your sequences, multiply them together, and for your probability, it depends whether we are talking about DNA level or protein level, so nucleotide or amino acid. In that scenario, it could be 1/4 or 1/20. Okay? Then you power it by the length, which is your interested length of matching. What do we mean by that? Like, for example, if I'm interested in length of a codon, we have 3 nucleotides. So the length is 3. Okay? So if I'm inside my sequence, I'm interested in just the length of a codon, and L in this formula should be 3. Now, sometimes we are interested in the expected length of a longest match. It means that I have a big sequence, like 1,000 number of nucleotides, and I'm interested to know about the expected number of match, like is 5 number of matches good enough? So it means that in the second sequence, exactly I should have A, C, D, C, C. So we have exact match of length 5. But is it meaningful? Is it good enough? Because I have 1,000 number of nucleotides, so maybe it could happen even by random, you know? So is it good enough or not? That's why it's very interesting for us to find out about expected length of the longest match. That's what we call it, and we denote by R. And why is it important? Because, as I said, we should know whether this number that we find at the end is meaningful or not. So what's the formula to find it? Logarithm based on, this is the base of the logarithm, 1/p. What was p? Exactly the probability that we talked about. And the length of m, length of S1, which is m, and length of S2, which is n. So we talked about p-value and expected value so far. Let's compare them together. Both of them are useful. For sure, they give us some information, but which one is better? We cannot say. At least scientists, they don't have common voice which one is better. I personally believe that p-value is better. Why is that? Because there are a variety of suggested formulas based on scoring matrices of the sequence alignment. So far, you have faced so many of them. And I even avoid to just giving you information about various algorithms as to memorize the name of them, for example, and exactly use their methods. Introduce you different algorithms. Even some of them are known, but at the end, I keep telling you that it's better that you find out your own algorithm. If you want to rely on the algorithms which they already use on their database, then what's the novelty of your work? You don't find new things in science if you just want to rely on them. Of course, we use the known algorithms in order to learn about how it works. But at the end, we are interested into constructing our own way of sequence alignment. For example, we use dynamic programming, which is frequently used. We talked about it, but you can even find better algorithm. Why not? So the thing is that, as you understood, there are a variety of them. There are so many of them. And that's why the expected value that you will find relies on them. When we talk about p-values is are defined based on a statistical background. And if you try to somehow relate it to normal distribution or other known distribution, then this is a solid way of comparing two sequence alignment together. If you find the optimal answer, then this is the way. This is the best way, the most scientific way in order to compare them together. That's why I prefer p-values. And of course, a scientist sometimes makes some mistakes, like when can I use a normal distribution? When can I use other distribution? And unfortunately, this is common. Even in scientific conferences, it happens a lot when we participate as a statistician. When you see some of the works which already published, unfortunately, in other sciences, then you understand some scientists unfortunately use the wrong distribution. And that's why it's very important to know about the statistic before using it in our scientific work. Like, when can I use normal distribution? It's not always that I can use that one. And when we talk about normal distribution in our courses and how we can approximate it, we talked about the size of your sample. And for example, we say if this is equal or more than 30, this is good enough to approximate my distribution with normal distribution. When this is less than 30, what about this one? They introduce different distribution, like t-student distribution. Not always I can use this one, because first I should prove that my population has normal distribution. Otherwise, I should follow non-parametric methods. So this is very important. Unfortunately, many scientists neglect that. And this is natural because, for example, as a mathematician, as a computer scientist, maybe I make so many mistakes in terms of biology because I'm not a biologist, or for example, psychology. So a biologist or psychologist can correct me. And the same situation here, if a molecular biologist is using statistics, unfortunately, they may make some mistakes. And if they publish their work in a molecular biology journal, it doesn't mean this is 100% true, because the reviewer maybe didn't have a good background in a statistic either. So such mistakes happens a lot, especially the science which is new, like bioinformatics. Bioinformatics happened when we gather lots of data, and molecular biologists couldn't handle them themselves, and computer scientists couldn't do it without getting the help from molecular biologists, because we are not biologists. So they started to have teams, like a collaboration between computer scientists and molecular biologists, and other sciences like applied mathematics or statistics. In the first session, I already talked about it, why they are related to each other. So then they decided to even define a new field, bioinformatics. And we are new in this. That's why we should get it better and better. That's why you see that there are lots of algorithms, and still we cannot say which one is the best. We should, for example, even talk about p-value and expected value and how we can compare them. So that's totally natural, what is happening. So I will talk about this specific scoring metrics on Wednesday. Let's have 10 minutes break, and I will talk about your weekly assignments. If if you have any questions, don't hesitate to type it on public chat. Then I will answer them from 10 minutes later for sure.